Good afternoon, everyone. I'm Annus Zulfiqar from the University of Michigan, Ann Arbor, and I'm presenting SPLIT, Partitioned Decision Trees for Scalable Stateful Inference at Line Rate. So as modern networks are pushing the limits of speed and scale, machine learning is increasingly being deployed in programmable data planes, including switches and SmartNICs, to enable real-time traffic classification, anomaly detection, congestion control, and adaptive bitrate streaming, all running at line rate. But why do we need ML in network systems? It's because ML enables networks to move beyond static rules by learning patterns directly from traffic data to make predictive decisions in real time. We have deep reinforcement learning that enables systems to adapt to changing network conditions using feedback. We have language models that we are exploring for network management tasks like network automation and troubleshooting. And we also have deep neural networks that enable high accuracy prediction by learning complex nonlinear patterns from data. To support all this, there is a growing body of research that has explored applying different ML techniques in networking, but these models come with significant deployment challenges because they typically require specialized accelerators like GPUs or TPUs, and they rely on floating point and matrix compute units for inference. So instead, when it comes to programmable hardware, decision tree models have been more widely adopted in existing systems. Because they are interpretable and easy to verify, their hierarchical decisions align with the match action table architecture. They use simple comparisons that can be mapped to TCAM and SRAM rules, and feature collection can be performed using stateful ALUs, which leverage registers to compute and maintain per flow state. A line of work has explored the feasibility of deploying decision tree models in programmable data planes, and they all primarily address the challenge of rule explosion by optimizing model representation, by using techniques like pruning the decision tree and compressing the match action table rules. But to highlight the key challenge in all these existing approaches, let me first show you how these baselines perform inference in the data plane today. These systems, all of them, they treat the switch as a spatially mapped architecture, where both feature collection and inference must be completed in a single pass in a one-shot manner to classify any given network flow. So in this example, we are assuming that the decision tree you see at the top is what we want to offload onto a programmable hardware that has 6 pipeline stages. The first step is to offload the model rules into the switch as TCAM or SRAM rules. These rules will encode the decision logic of the model directly in the data plane. So for example, for these rules, we are assuming that they will occupy the last 3 stages of the pipeline. So with that, we have only the first 3 stages left behind for feature calculation and storage, which means that we are capable of storing at most only top K features, or in this case, top 3 features, to sustain the desired number of flows that we want to accommodate on the hardware, which is dictated by the memory available in each pipeline stage. So these kind of traditional schemes, they have relied on spatially mapped architecture. They constrain us to perform one-shot feature collection and inference because they are limited number of features that can fit in the switch registers at any time. And ultimately, this prevents the model from reaching its full accuracy potential because it cannot leverage richer, more informative stateful features. To make this limitation more concrete, we compare top K features against an ideal model. The red curve that you see here shows a top K based model, which is running in the data plane under the constraints of the hardware. So we only have a limited number of features. The dashed line that you see at the top represents the ideal case, which has no stateful memory limitation, so it has access to all the features. What we observe is a clear gap between the two in terms of F1 scores for any given number of flows. And this highlights the core limitation that restricting the model to a small subset of features will always prevent it from reaching its full accuracy. SPLIT, what you see here in the blue curve, is bridging this gap by enabling access to more features, improving the accuracy beyond traditional top K model-based approaches. So let's see how SPLIT does this by rethinking inference as a time-shared process rather than a single pass execution. Instead of computing and storing all the features upfront, the model is divided into partitions, where each partition contains multiple subtrees that operate on their own top K features. As the first window of a flow arrives at the switch, only the features that are required by the active subtree are computed at any given time. We then make a partial inference. but not to label the packet into a given class, let's say benign or malicious, but to determine what should be the next subtree selected in the subsequent partition that should be activated for only this given flow. Once inference is complete and the next subtree is determined, we recirculate a single packet in the switch, which serves as an in-band control channel to update the active subtree ID, which activates the corresponding subtree for that flow. What does it mean for a subtree to be activated? Well, it means that now the incoming flow will be looking at a different portion of the decision tree, but more importantly, the system will now begin to collect a completely different set of top K features which are required by this newly activated subtree, a small portion of the decision tree. By recirculating this packet, we are effectively resetting the execution context in the switch and preparing it for the next stage of inference. As the next window of packets for the flow arrives at the switch, the system begins collecting the next set of required features for this newly activated subtree. And once feature collection for that window is complete, we perform another partial inference which determines the next subtree to activate for this decision tree. A packet is again recirculated, registers are cleared again, and now we are ready to compute the next 3 features. Once again, the features are collected for another window of packets, and recirculated packet again resets the state for the next active subtree. So as a result, now the stage is set to activate the collection of the last 3 features in our terminal partition. When now we perform inference on this subtree, we get our final classification for our flow, which in this case is evaluated to be a malicious flow. So you can see that using the same switch resources while sustaining the same number of flows, we can now support significantly more features instead of just the top K across the entire decision tree, which is imposed by traditional implementations. Just by rethinking the switch as a time shared machine, we are able to increase the total feature count to 12 in this case. In our experiments, we have shown that by enabling this kind of a design, we are able to increase our feature capacity for this kind of partition decision trees by up to 5-folds. Now let's dive deep into the key design challenges of our partitioned approach and how we overcome them in SPLIT. First, the decision tree has to be divided into these multiple partitions. So what is an optimal partitioning strategy? Second, inference is being performed at window level and not flow level. So some kind of custom training is needed for this kind of a decision tree. Third, throughout this design, we are relying on windows of packets for inference, and we'll see shortly for the same for training. So what should be the size of these windows if you're not looking at the entire flows? And finally, we are heavily using recirculation. So can we constrain this design to within the limits imposed by current data planes? So let's start with the first question. We will look at the key elements that define a partitioned model. First, a decision tree can be partitioned in a number of ways. So imagine that you're placing this kind of arbitrary cuts at different levels of the original big tree. What we realized in our experiments is that the optimal strategy depends on the kind of application that you're working with, the data set itself. Some benefit from having deeper early partitions to enable better routing and subtree selection in the subsequent partitions. Others benefit from deeper final partitions for more precise classification at the very end. And there are applications which benefit more from having balanced sizes of all partitions. The number of possible ways to cut a tree that has depth d is given by 2 raised to power d minus 1. In our design, to obtain the optimal partition model, we perform a design space exploration over 3 key parameters: the total tree depth, the partitioning strategy, and the maximum features or K that we want to select per subtree. We formulate this as a multi-objective optimization problem where we want to maximize both the F1 score and the number of supported flows in the data plane while staying within the hardware constraints such as our available register space, total number of rules that can fit in there, and the recirculation bandwidth. To solve this search in an efficient manner, we use Bayesian optimization. In each iteration, we provide 3 search parameters along with the optimization objectives and the hardware constraints. Using these parameters, we train the partition trees using a custom algorithm using windows of training and test data sets. After this step, we encode the subtrees as TCAM and SRAM based rules. Once the rules are calculated, we determine how much of the pipeline is still available for subtree level feature collection. This enables resource estimation, where we compute the number of flows that can be supported based on register capacity, along with recirculation bandwidth. As a final step, we determine the feasibility of the model along with the F1 score that we received, and we feed both back to our Bayesian search to inform it about the current model's feasibility against our optimization objectives so that it can guide the next iteration of search. Once an optimal configuration is found, one that maximizes both the F1 score and the number of flows that we are accommodating, we generate the corresponding TCAM rules and the data plane binary required to deploy our model on the switch or the SmartNIC. Here we are showing the mean time that is taken by each stage of our search framework across different data sets. Training, you can see, is the most time-intensive component among the framework modules. However, even that takes roughly 4 to 4.5 minutes per iteration on average. Overall, we observed that the average time per iteration is roughly 300 seconds or about 5 minutes. We also estimated the total number of iterations needed for our search to converge for all of our data sets. In the worst case, we need about 150 iterations, but for most of the data sets, the search converges within just a couple of hours and automatically discovers the models that maximize both the F1 score and flow scalability. Moving on to our next question, how should we train this kind of partitioned decision trees? Our Bayesian optimization framework that I showed earlier already incorporates this step, so let's take a closer look at that. We start at the very root of our overall decision tree and train it using the first window of each flow, but only that specific subtree, not the entire decision tree, and limit it to its own top K features. The first subtree will then route each of those flows to their respective subtrees through one of their leaf nodes, where we use the next window of the flows and its own top K features to train the subtrees in this second partition. We repeat this training step recursively for each subsequent layer, training subtrees using corresponding flow windows until all subtrees in all of our N partitions are trained using their corresponding flow window samples. And you can notice that all the subtrees are trained on a specific distribution of flow windows that they should expect to receive at runtime. So as a result, our training mirrors how model executes in the switch. Moving on to our third question, what should be the ideal size of these flow windows? We said previously in our execution that each partition requires a window for inference, and now we have done the same thing with training. In our design, we have restricted the flow windows to be uniformly sized for any given flow across partitions. An equal sized window first, across the partition, would ensure that each tree partition gets an equal amount of data to make accurate inference decisions. But more importantly, we keep these window sizes equal in order to avoid blowing up our design space, because the sweep space of having non-uniform flow windows can be quite huge. If we allowed this kind of variable windows, that would add another parameter and make the search much more complex, probably exponentially more expensive. Keeping them constant, we simplify the optimization while still achieving Pareto trade-offs in our results. About our last question, what about the recirculation bandwidth? If we go back and recall our example that we considered, for a partition size of 4, only 3 packets were recirculated regardless of the size of the flow that you're receiving. In our evaluation, we found that for 2 types of data center environments here, web server and Hadoop, across 3 different data sets, we require negligible recirculation bandwidth. And that's because regardless of how much traffic you're receiving at line rate into your switch, only a small number of packets on the order of number of partitions are recirculated, which is orders of magnitude smaller than your line rate traffic. With all our design concerns addressed, let us see how different components of SPLIT come together to deliver strong results. We use these 7 different datasets for our evaluations that span IoT traffic classification, VPN identification, and network intrusion detection. I will show the results corresponding to D1 to D3, but all the datasets show similar trends. First, we are looking at F1 score versus flow scalability. How many flows can be supported in the data plane? Each point on these plots represents a feasible model under the switch constraints, and we are looking at 2 state-of-the-art approaches here called NetBeacon and Leo. SPLIT, shown in blue here, consistently achieves a superior Pareto trade-off, delivering much higher F1 scores at each flow count compared to the baselines, because it can utilize much more features compared to these kind of top K based schemes. Next, we are showing flow level time to detection on real world data center traffic environments. SPLIT, you can see here, achieves performance comparable to the baselines across all flow sizes. Because even with partitioned inference, we don't introduce any additional delay in the system, maintaining fast and responsive detection while improving accuracy and scalability. We further evaluated our performance by looking at the trade-off between TCAM budget that is available and the maximum F1 score that you can get from any of these models. For a fixed TCAM budget, SPLIT consistently delivers higher F1 scores compared to baselines. And finally, we evaluated how register memory scales with the number of features. On the x-axis, you see the total number of features that any model can support across the entire decision tree. And on the y-axis, you see the register bits needed to represent a single flow. The different SPLIT lines here labeled SPLIT 1 to SPLIT 4 correspond to configurations with increasing top k, the k for any given subtree. What we observe here is that SPLIT configurations remain flat, maintaining constant memory usage as the total number of features increases. So this highlights a key advantage of SPLIT, that it can decouple feature space of the entire model from physical memory utilization, allowing us to scale to many more features under the same hardware constraints. To summarize, SPLIT supports 5x more stateful features than state-of-the-art DT implementations in the data plane, enables richer, more accurate in-network inference, all while maintaining low recirculation overhead and comparable flow level time to detection. Thank you for your time, and now I'm open for any questions.